All right, welcome in. This is our chapter 4 material on chemical equilibrium. In this chapter, we will introduce the idea of equilibrium, equilibrium constants, and the law of mass action. We will also introduce our calculation technique for equilibrium problems, and then shift away and talk about some more conceptual ways to consider equilibrium using Le Chatelier's principle. All right, let's get into it. Chemical equilibrium is this idea that when you have reversible reactions, you will have both directions of that reaction going at the same time. Eventually, if both the forward and the reverse reactions are going, you might reach a state where they are going at the same rate. This is called equilibrium, where the forward and the reverse reactions are occurring simultaneously and at the same rate. In our equilibrium state, we will end up with some mixture of reactants and products because, well, we'll always be forming some of our reactants again. We'll never have 100% product. We can visualize this with our slinky going down the escalator in the top right of the screen. If you have a slinky and you just time it perfectly, sending it down the escalator, well, the slinky's going down, the escalator is rising up. And if you look at this from afar, it appears like the slinky is just remaining completely stationary. Here we have our forward and reverse rates going the same rate, and something similar happens for our chemical reaction. In our chemical reactions, we do have both the product and the reactant present at the same time. They might not be the same amounts, but they're both present. Here's what this might look like. If we have a reaction of N2O4 decomposing into two NO2s, well, initially, maybe we have only our reactant, N2O4. As it reacts, some of those products will start to form. When we have some of those products there, well, they can also react and form our reactants once again. After some amount of time, the composition will reach some steady state where we have some of these products and some of those reactants. We can look at this graphically. Here are the concentrations of our chemicals. Initially, we have lots of our reactant and none of our products. That reactant gets consumed as our product gets formed. Once we reach our equilibrium, we'll have the same amount of our reactant and the same amount of our product from that time forward. Those amounts are different, but they're not changing. We can also examine this in terms of reaction rates. For our forward reaction, maybe the reaction rate has a rate law of K times N2O4. Initially, we have a lot of that reactant, and so the rate is relatively high. As that reactant disappears, our rate will decrease. Alternatively, our product can go back into the reactant. NO2 can turn back into our N2O4. And the rate for this reverse process can be some rate constant times NO2 perhaps squared, if this is an elementary step. Initially, we have none of our product, so the rate is exactly 0. But as more of it shows up, that rate will slowly increase. Our equilibrium state has those rates no longer changing. And in fact, the rates are equal and opposite. So one more time, our concentrations at equilibrium are not changing, but they might be different from each other. Our rates at equilibrium are also not changing, but equilibrium is the state where the forward rate and the reverse rate are exactly the same. Another way to picture this, we can use our reaction coordinate. If we have this given reaction, we need to climb over this activation energy to reach our products. To do the reverse reaction, we need to climb over a slightly different activation energy in order to get back to the reactant. the relative activation energies for that forward and reverse reaction will dictate how fast they go. Likewise, our concentrations will also dictate how fast our reactions go. We can summarize this with our skills from our kinetics lessons, using our rate laws and perhaps the Arrhenius equation to relate how fast these reactions are going to their relative concentrations, rate constants, frequency factors, and activation. Because these activation energies are different for the forward and reverse reactions, we can have different amounts of our reactants and products once we reach that equilibrium state. We can present this another way. We can call this the law of mass action, right? If we're thinking about the rate of our forward reaction and the rate of a reverse reaction being equal to each other, sure, we can tie these two rate laws together, but maybe we can rearrange this to have all of these concentrations on one side of the equation and all of the rate constants on the other side of the equation. So here, our relative products and reactants are related to our relative rate constants for the forward and reverse reaction. We can be a little bit more general. Maybe we have some coefficients. If we do, those coefficients, at least for elementary steps, will show up as exponents in our rate law. And if we combine all of the concentrations together on one side of the equation, we can end up with this expression. The concentrations of our products raised to their coefficients divided by the concentration of our reactants raised to their coefficients is equal to some combination of rate constants. We'll call this capital K. We'll call this the equilibrium constant. Subscript C refers to concentration. This is the law of mass action. Our equilibrium constant is equal to our concentration of products divided by reactants. Coefficients turn into exponents. A wrinkle for our equilibrium constants, for our law of mass action expression. We're only going to include things where the concentration might actually change. If we have a solid or a liquid, these condensed phases don't experience meaningful concentration changes. For reasons maybe a little bit beyond the scope of this course, we're not going to include our solids or liquids in that equilibrium constant expression. We are going to include gases, and we are going to include aqueous species. We can try to get some practice here. Take a moment, see if we can get some of these, and we'll talk about a handful of them together. All right, for this first reaction, we have two COs combining with an O2. Well, we can go the equilibrium constant in terms of concentrations is equal to our products divided by reactants. We have CO2 as a product, and it has a coefficient of 2. That 2 turns into an exponent. Our reactants, we have carbon monoxide with a coefficient also of 2. And we have oxygen without any coefficients. Notably, all of these are in the gas phase, so they all get included in our expression. If we want to try the third of our problems, we can say our equilibrium constant expression is equal to products divided by reactants. Our products, we have iron, but this is a solid. Just leave it out. We do not need that. We also have carbon dioxide as a gas. We will include this. We'll divide by our reactants. We have iron 2 oxide, but again, this is a solid. Just ignore it. We don't need it. We also have carbon monoxide. That does get included because it is a gas. All right, that is our law of mass action. That is our equilibrium constant. The equilibrium constant, as the name implies, is a constant for a given reaction at a given temperature. It has a numerical value, And since it is a ratio of molarities, it is going to be unitless. The relative size of our equilibrium constant tells us about the relative amounts of our chemicals once we reach that equilibrium. This is our products divided by the reactants, right? A ratio of how much products you have compared to how many reactants you have. If this ratio is bigger than 1, that means the numerator is bigger than the denominator. That means we have more products than reactants. Alternatively, if our K value is very small, we have a bigger denominator than numerator. This fraction being less than 1 implies we have more reactants than products. Another quick practice example. Okay, we're at equilibrium, we can find Kc. Step 1 is to write the equilibrium expression for this reaction. And then we can fill in our molarity value, moles divided by liters. We get something like this, and we can find a numerical value. 2.5 times 10 to the 4th power. This is something much, much bigger than 1. Our equilibrium position here favors the products. Another practice problem. Can we decide if the reactants or the products are favored? Well, to solve this, we just need to look at the magnitude of our equilibrium constant. This equilibrium constant is very large. It will favor the products. This equilibrium constant is very small, 10 to the negative 4th power on our equilibrium constant, tells us that this favors the reactants. Lastly, okay, another equilibrium constant, 10 to the positive 7th power. This is very large. This will also favor the products. A useful tool we can use is the reaction quotient. If our system is not at equilibrium, well, we can still write out the law of mass action. It just won't be equal to the equilibrium constant anymore. Instead, we can say that this is equal to the reaction quotient. The reaction quotient has the exact same form as the equilibrium constant, except, well, maybe we're at equilibrium, but we're probably not. We can compare our reaction quotient to our equilibrium constant to decide, are we at equilibrium or not? And to decide which way our reaction will have to proceed in order to reach that equilibrium. If we have a Q value that is too big, that means that we have too many products. The numerator is too large. If Q is too big, we will do the reverse reaction in order to reach equilibrium. Alternatively, if our Q value is too small, smaller than the equilibrium constant, that means we have, well, too much of this denominator, too much of our reactants, not enough of our products. If our Q value is too small, we will go forward until we reach that equilibrium state. What does it mean to be at equilibrium? Well, that's when our Q value is exactly equal to K. If you're someone who appreciates a good graph, we can picture this graphically. Here is the value of the equilibrium constant for some random reaction. And this curved line is our Q value, our reaction quotient. When we have Q equal to K, this is the one point when we're at equilibrium. If Q is too big, however, we have too many products. If Q is too small, then we have not enough product. Our reaction will always proceed until we reach that exact equilibrium point. All right, let's pause for another practice question. If we have our mass of our chemicals, can we figure out, well, which direction will the reaction proceed? Are we at equilibrium or not? To solve this, we want to compare our equilibrium constant to our reaction quotient. Right? Which one of these is bigger? We know the value of K is equal to 0.0108. Now we want to figure out our value of Q. Q has the same form as our equilibrium constant, so it's going to be our products divided by our reactants. In this case, our products are CO2, as, well, this is the gas that we care about. Our reactants are nothing, so Since these are solids, we can just leave them out. If we want, we can just erase this divided by 1. And so we can say our Q is going to be the concentration of CO2. What do we have? We have 1.0 grams of CO2. We want to have the moles of CO2 divided by the liters of our container. So we can use our molar mass. We can use our volume. This is going to be our concentration of CO2. 1 gram divided by 44 grams per mole divided by 1 liter. Our Q has a value of 0.023. What's bigger, Q or K? Well, 0.023 is going to be bigger than 0.0108. Since our Q value is big, that means we have too many of our products, and we will go backwards in order to reach our equilibrium. The amount of calcium carbonate, that's our reactant, will increase in order to reach that equilibrium state. All right, now that we've had some practice with our equilibrium constant expression and with our reaction quotient, we can, well, give an alternate form for these ideas. We've looked at this in terms of concentration, but we can also use pressures, right? We can measure the partial pressure of each of our chemicals and write out the law of mass action, write out the equilibrium constant using those partial pressures. We still call this K for equilibrium constant, but now we change the subscript to P for pressures. So once again, for our general reaction, we have our products divided by our reactants, but now we're thinking about the partial pressures of our products raised to their coefficients, divided by the partial pressures of our reactants raised to their coefficients, and that is our law of mass action. This is useful for gas reactions. Again, we don't include solids or liquids in this law of mass action. Only gases really make sense here, but it is a nice, convenient way to deal with some gas reaction. If you're wondering about how our Kc and our Kp are related, well, it turns out they are related, and we can convert between the two of them. The way we do that is simply by utilizing the ideal gas law. The pressure is related to our molarity times the gas constant and the temperature. If you take your Kp expression and replace all of these pressures with molarity times RT, we can derive a new relationship between Kp and Kc. The answer here is Kp is equal to our Kc times parentheses RT raised to the delta N. In this equation, R is just the gas constant from the ideal gas law. T is the temperature in units of Kelvin. Delta N is a little bit weird. This is the moles of gas that are, well, the difference in moles of gas between our products and our reactants. Count up the moles of gas in the products based on the coefficients in our balanced reaction. Then subtract the moles of gas in our reactants based on the coefficients in our balanced reaction. Delta N is moles products minus moles reactants based on the coefficients. This is a little bit weird. Let's try a practice problem. Here we know that Kp is equal to some value. We want to find Kc. We can use our equation. Kp is equal to some number. Kc is the one we're trying to find. R, we know. The temperature, okay, we tell you the temperature is 298 Kelvin. Delta N. Let's figure out delta N. On the product side, we have 1 CO and we have 3 H2s. These are all gases. We have 4 moles in the gas phase. On the reactant side, we have 1 CH4, we have 1 H2O. That's a total of 2 moles in the gas phase. delta N is going to be equal to 4 minus 2. Pull out the calculator. Delta N is just 2. If we want to solve for our Kc, we can say that this is 7.7 times 10 to the 24th divided by 0.0821 times 298. This whole thing raised to the second power. Our Kc is going to be about 1.3 times 10 to the 22nd. For this second practice problem, we can do something similar. Here we have 2 moles in the gas phase on the reactant side, and we have 2 moles of our gas phase on the product side. Delta N here is going to be equal to 0. And so in our equation, if we have delta N is equal to 0, RT raised to the 0th power is exactly just 1. And so we can say that Kp is just exactly equal to Kc. Sometimes that's the case when we have equal moles of gas on each side of the reaction. One last skill we can introduce here, if we have our equilibrium constants. Well, we can think about what happens to our equilibrium constants if we manipulate our reactions. If you reverse a reaction, well, we flip our reactants to the products and vice versa. In terms of the equilibrium constant expression, this is exactly the same as our forward reaction, except inverted, flipped upside down. If you reverse a reaction, you're going to invert the equilibrium constant, raise it to the -1 power. Cool. All right. What else can we do? What if we add multiple reactions together? Here's a simple example. A goes to B. B goes to C. Our total reaction, if we add together these first 2 steps, A turns into C. Well, we can visualize this. For that first reaction, we have, B over A. For our second reaction, we have C over B. For the overall reaction, we have C over A. How is this equilibrium constant related to these first 2? Well, it's just the product of those first 2 equilibrium constants. And this is going to be true in general, even for more complex reactions. Whenever you add 2 reactions together, you can make a new third reaction, which has an equilibrium constant equal to the product for the equilibrium constant of each reaction that you added together. Adding reactions, multiply the equilibrium constant. A bonus thought here, what if we were doubling a reaction? Well, doubling a reaction is the same thing as adding a reaction with itself at least one time. If you add a reaction to itself, you'll multiply the equilibrium constant by that same equilibrium constant. If you double a reaction, then you'll have to square the equilibrium constant. All right, one last practice problem, then we can wrap it up for this video. We're asked to find Kc for our reaction. We're given a couple of other reactions. Can we combine these 2 together to build the reaction that we care about? For these types of problems, I like to look for one of the chemicals that we want inside of our potential mechanism reaction. If we're trying to build 2 NOs, well, we have that in reaction A. So we can say reaction A, let's leave that one as it is. Then we can look for another target molecule. Maybe we're trying to start with 2 NOs. Well, that shows up in our mechanism steps down here. Reaction B, it seems like our chemical is on the wrong side. Looks like we might need to flip that reaction. If we flip reaction B and then add it with reaction A, do we build the reaction that we care about? I think so. We can write out reaction B backwards add it to reaction A written forwards, and convince yourself that this is true. If that's the case, great. What do we want to do? We want to take our equilibrium constant for step A, leave it exactly as it is. We want to take our equilibrium constant for step B, and we need to flip the reaction, so invert the equilibrium constant. Then we add these two reactions together, so we need to multiply their equilibrium constant. The equilibrium constant for the overall reaction, therefore, is going to be Ka times Kb to the -1 power. And here my notation, this one is Ka, this one is Kb. This overall reaction that we're asked about has an extremely small equilibrium constant. There are going to be very little products and mostly our reactants once we reach that equilibrium state. All right, I hope this has been helpful. We've introduced the idea of equilibrium and have some new skills that we can use. Please come back for the next video. I'm looking forward to seeing you there. We'll introduce our calculations and also some conceptual ideas. But in the meantime, let me know if you have any questions, and have a great day.